Hi everyone, this is Yutian. Today I'm going to talk about our research on combining electroencephalography and diffuse optical tomography enhances spatial temporal resolution of reconstructed neuronal activity in auditory cortex. Electroencephalography, also known as EEG, works by measuring the voltages on the skull. It has high temporal resolution in the order of milliseconds, but low spatial resolution in the order of centimeters, because the EEG electrodes are measuring the voltages that go through layers of brain tissues. On the other hand, diffuse optical tomography, also known as DOT, is a kind of high-density near-infrared spectroscopy. It has high spatial resolution in the order of millimeters, but low temporal resolution in the order of seconds, because DOT works by measuring the hemodynamic responses, whose duration is around 10 seconds. So if we can combine the two advantages of EEG and DOT together, we can get high spatial temporal resolution at the same time. Our previous research conducted by Dr. Jiaming Cao has proved that in the visual cortex, if we can combine the DOT reconstruction together with the EEG reconstruction, we can get neural activity reconstructions with high spatial resolution and keep the sensitivity in time to show the neural activity responses to stimuli appear at different time points in an experiment. So the algorithm works well for shallow neural activities. But if the neural sources are deeper, does the algorithm still work? To study this question, we move from the visual cortex to the auditory cortex in the temporal lobe. Specifically, we choose the sulcus between the superior temporal gyrus and the middle temporal gyrus as our region of interest. Here, we can move our neural sources to different depths. So let's look at the DOT reconstruction of sources with different depths first. Zooming to the sulcus, we can see that the neural sources are moving deeper and deeper. Correspondingly, the DOT reconstruction, which will be used as a spatial prior later, is becoming more and more diffuse when the source is deeper. So what would happen if we use this result to help the EEG reconstruction? Here we are showing two examples of the DOT prior EEG reconstruction. On the top is a shallow neural activity source with a depth of 13 millimeters, and on the bottom is a source with a depth of 18 millimeters. If we only look at the EEG reconstruction, we can see that the deeper the source is, the more spreading the reconstruction will be. And yes, there are some negative errors in the 18 millimeter example. That is because the dipole orientation of the deeper source is a little bit different from the shallow source. But if we look at the DOT reconstruction, we can see that for both examples, the DOT reconstructions are more concentrated and it can capture more depth information compared with the EEG reconstruction only. Combining the EEG and DOT reconstruction together, we can see that the joint reconstruction has higher spatial resolution as both of them are more concentrated and in the correct location, referring to the ground truth. In conclusion, DOT prior enhances the spatial resolution of EEG reconstruction for neuronal activities in the auditory cortex, and the resolution of DOT prior decreases as the depth of neuronal sources increases. For the future work, we are going to develop and apply algorithms to optimize the joint EEG-DOT reconstruction for deep neural activities. And we are going to apply the algorithm to experiments for neuronal activity measurements with high spatial temporal resolution in the auditory cortex. And thanks my labs for all the help, and thank you very much for listening.